First part is the integral test, and the second part is the p-series test. Well, this is going to be very well connected with what we did before in improper integrals. So notice how we went about the convergence and divergence of these integrals, of these improper integrals. We looked at different cases for type 1, 3 different cases, and then type 2, which we had, like a discontinuity at either one of the limits or somewhere in between the limits of integration. Well, at the end of the section, we summarized, or rather we came up with the p-integrals, which were integrals that look like 1 over x to the p power with respect to x. So in a similar way, we're going to do something similar but with series. So let's see. So the p-series test, so we're going to have a series of the form 1 over n to the p power, and that, all we have to do is observe that value of p. And if that number, or that power p is greater than 1, well, the series converges. But otherwise, if that value of p is less than or equal to 1, this series will diverge. It's actually exactly the same idea as with the improper integrals, right? We observe the integral. If that power p had the same criteria for that power p. So in a way, this is really nothing new, except that the context is about infinite series, right? Because in the integral test, we use the integral, the convergence or divergence of the integral to determine the convergence or divergence of the series. So in the same way, using the p-integrals, so we are using the p-integrals to conclude about p-series. But in this case, we will not even write a p-integral. Why? Because we can just use the same result. All right. So we have a couple of examples here for which we will have to determine the convergence or divergence of this p-series. So for the first example, sigma n equals 1 to infinity, 1 over n squared, what do we have? P equals to 2. But in this case, since this number is greater than 1, this is a convergent. This converges actually. That's it. We don't have to find any limit. We don't have to compute anything. Just observe the value of p. And well, that's like the nicest case in which we have the series in the required form. However, like letter B, that may need some rewriting first. Like, well, sigma n equals 1 to infinity, 1 over the square root of n. Well, so we need to change this radical form into a rational expression form. And in this case, p equals to 1/2, but in this case 1/2 happens to be a number less than or equal to 1. So for this reason, this series diverges. All right. What about letter C? Well, letter C is sigma n equals 2 to infinity and to the negative 1.001. So this is the same as saying sigma n equals 2 to infinity 1 over n to the 1.001. So we need to write this series in the form 1 over n to the p power. Well, if we observe the number 1.001, p equals to 1.001, this number, just because of the decimal 0.001, that's going to make a huge difference. That's the difference between having our series to converge or diverge. And in fact, because this number is greater than 1, that's going to be a convergent series. All right. As easy as that. Yes?
Do we have to change it starts at n equals 2?
It doesn't matter. No, it does. It ultimately doesn't matter. So we can have a. That's a good question because we can for some series, I mean, the one you want to start at 0 only is when you have a geometric series in the case that it converges and that's in order to find the infinite sum in the convergent case. So we can use the same formula that we have, all right? But in other cases, it doesn't matter because, I mean, this infinite series, we're looking at their behavior, I mean, in the long run, for large values of n. So the first few terms really don't matter, right? And well, the next is a typical exam question. So you are given this series in symbols. They're not asking you, determine whether that series converges or diverges. How long did it take us to find the convergence or divergence of the series? Basically seconds, right? Like the first one, a couple of seconds by just looking at the power. Okay, 2 is that greater than 1? Converge, right? I think it took us writing it down longer than just thinking about it. However, well, in this case, they're asking us for which values of A we will have a convergent series. So, well, recall that a P series converges when P is greater than 1. That is, in this case, we have to set this quantity 3a plus 2 because that will be our n to the p power if we set this 3n plus 2 our p. So in this case, if 3a plus 2 is greater than 1, so all we need to do is solve this inequality for a. So subtract 2 to get 3a greater than -1 and a greater than -1/3 by dividing both sides by 3, which in interval notation, that's -1/3 to infinity. That is, any number between -1/3 actually exclusive because of the inequality symbol and the parentheses, and anything larger than that, plug it in A in our series, that should give you a convergent series. All right, for example, let's do some simple cases. So how about A equals to 0? Well, A equals to 0 is a number within -1/3 and infinity, so that should give us a convergent series. All right, so sigma n equals 1 to infinity. So that's 1 over n to the 3 times 0, which is 0 plus 2, n squared. Isn't that a convergent P series? Yes. What about A equals to 1? This is sigma. I'm just going to skip the limits. 1 over 3 times 1, which is 3 plus 2. Isn't that P greater than 1? All right. Okay, I'm going to choose a number outside of this, of this interval. So that's A equals to -1. All right. That's a number outside of the interval. So that should be sigma. Okay, 3 times -1. That's -3 plus 2, -1. But -1, it's a number less than or equal to 1, so that's a divergent series. And that's because I chose a number outside of the convergence interval, right? Actually, well, just to give you like, a little bit of vocabulary for later, this is basically the interval of convergence of the series. But we're going to look at that for a series that contain x, so far all the series that we've been working with are just algebraic or numerical series. Notice we don't have any x's at all. All right, it's all numbers. But later in the last couple of sections, we're going to look at series that contain x, and we are going to find their domains in a way. But those domains are really the intervals where we can have a convergence here, but that's for later. In the meantime, Let's look at a comparison test. All right? Let's look at the comparison test. So that's 11.4. All right. What do we have for now? So far we have number one, the telescopic series that can give us the infinite sum. The geometric series that can give us the infinite sum in the convergence case. All right. What do we have? What else do we have? The n-term test for divergence. And in the previous section, we'll learn two more techniques. Number one, the integral test and the p-series test. So far, we have 5 tests out of the 10 that we are supposed to learn. All right. Today we're going to learn 2 more. Number one, the direct comparison test and the limit comparison test. All right. So this time for direct comparison test, we're going to look at series that look more complex, for which, well, you don't want to try the integral test on the first one unless you want to do a big partial fraction decomposition problem. Good luck with that. It's doable though, but that's not the most efficient way to go about it. All right. The second series, well, I don't think there's a way to integrate that one. Maybe, but I don't think so. And same with the third series. No, so you don't want to overwhelm yourself and find and do something very complicated. So instead, we're going to look at this series and obtain a simpler series that behaves similarly. So what do we mean by that? Well, number one, so out of this madness that we have here, so this series looks like what and how do we do that? Well, notice that for polynomial functions and rational functions, which is really polynomial over polynomial, the end behavior is pretty much given by the leading terms, all right? So really these 3n minus 5 or this negative 4n cubed plus 7n minus 5 really don't, those terms really don't contribute that much to the end behavior of the function the same way that the leading term. So in a way, you can think of neglect all the lower degree terms and focus only on the highest degree terms. That's going to give us the following series. Sigma n equals 1 to infinity of n squared over n to the 5th power. And well, after some simplification, sigma n equals 1 to infinity 1 over n cubed. And what do we know about this series? It converges. This is a convergent p series, right? It's the n to the p power form. So this is the idea. Out of some madness given, we're going to come up with something easier to determine its convergence or divergence. Let's look at the next one. Sigma n equals 1 to infinity, the 1 over the 5th root of n cubed plus 2n plus 4. Well, this series looks like well, how about again we neglect all the lower degree terms, that is the 2n plus 4, and we just keep the highest degree term inside of the radical. Well, that's going to give us the following. So that's going to be sigma in n equals 1 to infinity of 1 over the 5th root of n cubed. And if we rewrite this radical form into rational expression form, we can make this look like a p-series, which is 1 over n to the 3/5. Well, in this case, this would be a divergent p-series again. So it's a p-series again, but in this case, this one diverges. All right. Let's look at another ugly looking series. So now we have 3 to the n over 7 to the n plus 9n minus 3. Well, in the previous examples, we were looking at the highest degree terms, right? That's because we had polynomials and in the numerator and denominator, or, well, for the second case, one inside of the radical. Well, in this case, for the third series, for the third example, we don't have just polynomials. So yes, we have a polynomial 9n minus 3, but we also have exponential function. So in this case, we're not going to look at the highest degree. In this case, we're going to compare the order of the functions, and in this case, the order, that is the order in increasing. In this case, well, it turns out that we have exponentials and polynomials, so the highest order functions are the exponentials. So in this case, we will neglect the lowest order terms, which is the polynomial terms. All right, and in this case, well, this series right here looks like sigma n equals 1 to infinity of 3n over 7 to the n, and that sigma n equals 1 to infinity 3/7 to the n power. All right, well, what about this series? It's geometric, and does that converge or diverge? It converges, right? So this is a convergent geometric. All right, it's a convergent geometric. So this is the idea about comparison test. So we're going to be given somehow ugly looking series. We need to come up with something a lot simpler so we can do that comparison. Well, so how are we going to compare this series? Well, so that's the definition below. So suppose we have two series. Number one, a series A sub n and a series B sub n. Now, number one, let's label each series before going through the details. This series A sub n, this is our problem series, or our mystery series, the one that we want to know its convergence or divergence, and usually it's going to be something not as straightforward as a geometric or as a P series. However, we're going to do something similar to what we did in the previous in the definition box above, which is come up with something that looks like the problem that is our test series, right? So, well, depending on the convergence or divergence, well, if we obtain a series that converges, well, so for convergence, if the test series convergence, then we need to show this inequality, which in other words is to show that tiny is less than small. Okay, this one is going to make sense with the examples. And likewise, if the other way around, if in this case we come up with a series that diverges instead, we would need to show the inequality the other way around, and in this case we wouldn't be showing that tiny is less than small. Instead, we will be showing that huge is greater than big. So right now this is a lot of symbols, a lot of ideas, but how about we go over some examples and make more sense out of all this definition box. All right. Okay, let's go by the next page. So let's determine whether each series converges or diverges. All right. So sigma n equals 1 to infinity of 1 over n squared plus 2. All right. Although there's another way to go about the series instead of the comparison test. Notice the form, it's 1 over u squared plus a squared. You can make that too as a quantity square and then use the integral test. And notice it's positive, it's decreasing, and what else? And it's continuous in the interval 1 to infinity. So the related function to that, it's a function that meets the three conditions for the integral test. But in this case, we're going to go a lot shorter than that. So, compare with and in this case, well, let's neglect this 2 because that 2 it's lower in degree than n squared. In fact, it's a 0 degree, it's a constant. So this looks like the series n equals 1 to infinity 1 over n squared. And well, we need to state the convergence or divergence of the simpler series, isn't it? Convergent P series. Alright, so this will be our mystery series, which is a sub n. This will be our test series, which is b sub n. Now, let's go back to the definition box. When we come up with something that converges, we need to show this inequality. In other words, the mystery series is less than or equal the test series. In other words, to show that tiny is less than small. Let's see if it's true for this case. Is it true that tiny is less than or equal to small? Alright, let's find out. So this will be our, oh, not yet, a sub n less than or equal b sub n. So a sub n is our mystery series, our original problem, and b sub n is our test series. Let's set up the inequality. So 1 over n squared plus 2, is that less than or equal to 1 over n squared? Is this inequality true? That's all you have to do. You don't have to do anything else. So here this is indeed tiny less than small. Maybe the tiny versus small, it's an exaggeration, but that's just so we can make a distinction between, well, these 2 in the denominator makes a larger number in the denominator, and when we divide by that number, of course that's going to become smaller in comparison with 1 over n squared. Yes, it's instead of saying smaller than small, well, let's call it tiny less than small, right? Because we were able to show this inequality, all we have to say about the original series is converges by DCT, where DCT stands for direct comparison test, right? So it converges. All right, that's how the direct comparison test works. Let's do another example. Another example, okay, sigma n equals 1 to infinity 1 over 3 plus 2 to the n. So let's see if we can come up with another series, something small, something similar, something simpler. So this to compare with. And again, we can neglect these 3, and this series looks like, essentially looks like sigma n equals 1 to infinity 1 over 2 to the n, which can be rewritten as 1 over n equals 1 to infinity. That's 1/2 to the n power. Okay? And well, so what do we know about this series? We've seen it a couple of times. And it's a convergent geometric, right? Well, because we came up with another convergent series, then again, we will have to show that tiny is less than or equal to small. In other words, a sub n, which is the mysterious series, is less than or equal b sub n, which is the test series. And again, this is our a sub n, this is our b sub n. All we do is set up the inequality in accordance with that. So, is 1 over 3 plus 2 to the n less than or equal to 1 over 2 to the n? Yes. That's all we have to do. That's it. So, about the original series, converges by direct comparison test. Alright, and that's it. So again, we managed to show that shiny is less than or equal to small. Can the test fail? Of course. I'll give you an example in which the test will fail. In the meantime, let's have a look at another example. So what do we have over here? So we have sigma n equals 1 to infinity, 1 over the square root of n minus 4. Alright? Well, let's see if we can come up with something simpler than this. So compare with sigma n equals 1 to infinity, 1 over the square root of n. And again, I'm neglecting the lower degree term, which in this case is a -4, that constant term. Well, so this is the same as saying sigma n equals 1 to infinity, 1 over n to the 1/2, and this is a divergent P series. Because this is 1 over n to the p power, and that power p is 1/2, and that number is less than or equal to 1, which falls in the category of divergence for this criteria in particular. Alright? Well, so in this case, because we came up with a divergent series, let's go back to our definition box in the previous page. So this time we will no longer show the inequality less than or equal, but actually greater than or equal, or in other words, we will show that huge is greater than big as opposed to showing tiny less than small. Let's see if this is true for this series. Well, so number one is, in this case, huge greater than or equal to big. In other words, is a sub n our mystery series greater than or equal b sub n our known series? Well, let's find out. Again, this is our a sub n and this is our b sub n. Well, so 1 over the square root of n minus 4, is this greater than or equal to 1 over the square root of n? Yes. Yes, that's all we have to do. That's all we have to show. This means the original series, what's going to happen this time? It diverges by comparison, because this time we managed to show huge is greater than big by comparing with a divergent series. So the original series will do exactly whatever the test series does, which in this case is to diverge. So diverges by direct comparison test. All right. Okay. Let's look at letter D. And letter D, it's a little similar. It's very similar to the previous example. It's very similar in the series that we're going to use to compare with. In fact, it's the same. So we're going to compare with sigma n equals 1 to infinity, 1 over the square root of n, which is the same as saying sigma n equals 1 to infinity, 1 over n to the 1/2, which in this case we know that this is a divergent P series. And because of divergence, because the known series is divergent, again, we will have to show that huge is greater than or equal to big. In other words, our mystery series is greater than or equal the known series. In other words, again, let's set it up. Is this quantity bigger than that quantity? Let's find out. So is 1 over the square root of n plus 4 greater than or equal 1 over the square root of n? Is this inequality true? No, so this is not equal. Well, conclusion, test fails or test inconclusive, exactly. Test fails or inconclusive. Alright, so we cannot use this argument in this case to show the divergence of the original series. Alright, so we have to go through a different test. Well, what would that test be? Well, potentially the integral test, make a crazy substitution for the given function, or the plan B for the direct comparison test. When the direct comparison test fails, that is, we're not able to show that tiny is less than small or that huge is greater than big, well, then we use the limit comparison test. And well, the first part of the limit comparison test will be exactly the same, in which we're given an ugly looking series. We need to get a simpler series, and that simpler series is easy to determine whether it converges or diverges. Question? So in this case, well, we're going to use that same piece of information, and in this case, well, so we're not going to set an inequality, tiny less than small, huge greater than big. So this time we're going to set a limit problem, and that limit problem is, number one, it's the limit of the ratio, that's a sub n, the problem, to the test, to the test series. Alright? So, and in this case, well, based on the final answer to the limit, if that final answer is number one, so two requisites. Number one, if it's a positive value and a finite number, then our original series will do exactly whatever the test series does, which in this case is either converge or diverge depending on what we get for the series. Alright? Okay, so let's look at one example. What do we have? 1 over sigma n equals 1 to infinity, or 1 over 2 to the n minus 1. Alright, so number one, let's come up with another series to compare with. And well, this looks like sigma n equals 1 to infinity, 1 over 2 to the n, which is sigma n equals 1 to infinity, 1/2 to the n power. Okay? And well, what do we know about this series? Is it convergent or divergent? Convergent, what kind of series? Geometric, right? So this is a convergent geometric. Alright, before doing the limit comparison test, let me do the direct comparison test. Ultimately, whether you use limit or direct comparison, the first step, which is coming up with the series to compare it with, it's exactly the same series. So let me show you why in this case there's no other way. Well, for now, there's no way than the limit comparison test. So that is, in this case, we would have to show for convergence that tiny is less than or equal to small. Alright? That means small, tiny is 1 over, that's the a sub n, less than or equal to b sub n. And that's 1 over 2 to the n minus 1, 1 over 2 to the n. Is that inequality true? No. Alright? In this case, it's not the case that this is not tiny and this is not small in comparison with each other this time. So this means that the test fails. So we need to go with the plan B, and the plan B is the limit comparison test. All right, how are we going to go about that limit comparison test? So in this case, we're going to set the limit a sub n over b sub n with as n approaches infinity, and that's the limit a sub n, which is the original series, 1 over 2 to the n minus 1 over the test series, 1 over 2 to the n. And well, yes, at the beginning, this is going to give rise to a complex fraction. But again, just make sure to delimit the fraction accordingly, right? And again, dividing by a fraction is the same as multiplying by the reciprocal, 2 to the n over 2 to the n minus 1. And let's go about this limit. And again, there's a few ways to go about this limit. However, first of all, we have to check this limit by direct substitution. That is, well, 2 to the infinity, that's infinity in the numerator, and 2 to the infinity, which is infinity minus 1, well, that minus 1 is not going to do any harm, so that's just infinity. This is good, because this means that we can do any algebraic technique to simplify this expression so we can compute the limit. That is, do any factoring technique, well, it's not going to work. Maybe rationalizing a denominator numerator, well, that's not going to work because we don't have any radicals. Maybe multiply by a conjugate, well, conjugate, that's when we use as well these radicals as well, so no, it's not going to work. So in this case we have a plan B, which is number 1, dividing, because this is an infinite limit, we can divide by the highest degree term in the denominator, but that's going to take some writing, or we can use the L'Hopital's rule. And I think that's shorter to use the L'Hopital's rule. But in this case, in order to use the L'Hopital rule, that implies finding the derivative of an exponential function or with a base other than e. Okay, I have a question over here. And okay, you have a question?
Why can't we use the leading coefficient?
That's another way. But that's kind of weird to see in this case, that because in this case this is not polynomial over polynomial, that's why we cannot really go with the leading coefficient. Question?
Never mind.
Okay. So let's review how do we find the derivative of an exponential function a to the u. That's the derivative of an exponential with a base other than e, and the derivative is a to the u du dx. That's if any mini chain rule, but in this case, as opposed to differentiating the e to the u, which is just e to the u, for a to the u we should multiply by ln of the base of the exponential function. So in this case, if we use the L'Hopital's rule, let me denote it here so that just so I can, so we're clear about what we're doing. L'Hopital's, so that's limit of the derivative of 2 to the n, which is itself 2 to the n times ln of 2, over the derivative in the denominator, which is itself, it's the same as in the numerator, ln of 2 to the n, but the derivative of -1 is 0. And as n approaches infinity, well, check this out. Check how these two divide out. Everything divides out, and in the end, what survives?
1.
We're left with a 1. So that's the limit. That's the answer to the limit. So there's a couple of things that we need to check about that limit. Number 1, is it positive? Is it finite? Well, then sigma n equals 1 to infinity, 1 over 2 to the n minus 1 converges by limit comparison test, LCT. We can abbreviate this to LCT. All right. And